Hello, am I audible? Hello, everyone. Hello, Hello. Hello.
Yes, Abhishek, you are audible.
Okay. Actually, my PC is running from the whole day to today, so now it was hanging a little bit, so I restarted it just. Hello, everyone. Sorry for this delay, guys. My PC just gave me trouble when I started the Teams. Okay, so let's start. Sorry for this delay. I'm just sharing my screen right now. I'm starting my virtual box. Okay. So hello everyone. So sorry for this delay. So today's session is very important. So today's session is on basic of how to make our own solver. So today we'll understand how we can make our own solver, how it is related to CFD, and like how the things are being done in the solver. For example, how we are discretizing the equation in the solver. How can we change various kind of solvers? So, in basic solvers we have uh, U equation, P equation, and we have to couple them using uh, we have Navier-Stokes equation, and we have to solve them by coupling with the help of projection method, pressure projection method, or different kinds of coupling. So these are partial differential equation, and they are basically non-linear partial differential equation. So OpenFOAM is basically made for solving fluid dynamics problem, which is based on finite volume method, right? But OpenFOAM also has capabilities to solve ordinary differential equation. So these ordinary differential equation can be used in some of the multiphysics problem. For example, if you have to solve some characteristic equation of a certain dynamic system which has like no linear ODE, or maybe which may be second order, third order, fourth order non-linear ODE. So the first we'll understand how we can solve a simple ordinary differential equation in open form environment. And when we'll have the idea of how the open form solve the simple ODE, then we'll move to the uh, a partial differential equation, which will be basically a heat conduction equation. First, we'll do a simple 2D heat conduction, then transient 2D heat conduction, then we'll move to the convection part. So basically today we will learn the basics of how we change the solver, how we modify it, and what are the precautions and important things that we have to take care while modifying it. Sorry. So first is this. So to show you how to solve an ODE in open form environment, I have taken a simple example of spring mass system. You all are familiar with that, and this is the equation of a spring mass system where m is the mass, C is the damping, K is stiffness of the spring. So now, because this is an ordinary differential equation, and if you, so you all know that for this equation, this is linear. If M, C, K are constant, then this is linear equation. And we all know that we have a analytical solution for that. But we want to solve it numerical. We want to see how things changes. So to solve it numerically, we have to convert it to this second order equation into like various number of multiple set of first order equation. So what we did is we introduce a new variable z, and we say that y is derivative of z, and z dash. So basically we have here two variable now. If you look at this equation, we have one variable that is z and second variable that is y. So we have given z a value, we have like assigned z a value that is derivative of y. So in this sense, we have like so if we like move forward, so we have z and y two variables, and we have two equation and two variables. So we can solve it by any finite difference method. So I hope you are, all guys are familiar with the finite difference method. If you are not, and the Taylor series, how it is done. If you are not, if you can like stop me, I'll Google some things and I'll show you. I hope you all are familiar. So this system of equation we can discretize. If we have to, if you want to numerically solve it, we have to discretize it. So we discretize using finite difference method, and that contains that to using forward Euler method. So this means is yn plus 1 is the time step that we want to calculate, and yn is the old time step we have the value of. So we have two variable here, y and z, and we iteratively solve until we get convergence and move ahead in the time step. So n is the old time step and n plus 1 is the next time test step that we want to calculate. So basically these two are the equation. So how solving an ODE is different from solving the Navier-Stokes equation, right? So this is the main question. So in when we want to solve this, so on the left hand side, what you see is the main function or the solver of simple form solver for the Navier-Stokes equation. Okay, so because in this case we have to have a mesh, so we have to have a set root case checking that whether the format of the folders is okay or not. Then we have to provide it with the control that which solver we want to solve and what is the time step. And then we solve the PD, right? And then we solve the PDE here, like there you see this U equation dot H. You see a while loop on the left, okay, which will run, which will solve until convergence and until we get the steady state basically. And you see hash include U equation dot H. So basically it is solving the U equation. Hash include P equation dot H is solving the P equation. All right. So it is iteratively coupling the momentum and mass equation using pressure. And that's where RPD is. Now, this folder that we have on the left, or this code interacts dynamically with the source file. So source file means where the all of the code is, like for the dynamic mesh, if there is a dynamic mesh, or the code for the discretization scheme, and the which kind of solver we want to use for iterative calculations. All right. So but in this, so this is for solving, so this is for solving Navier-Stokes in which we have mesh. But when we're solving a ODE, we don't need a mesh. So this is basically a simple time-wise. This ODE is simple where we have to find, there is only one independent variable, that is time. So there is no mesh. So for that, we have to have your application or a solver, a linear oscillator, and that is coupled with the source code. Now I'll just show you how it is done. So what we'll do here is, let's move ahead. After this, on the left hand side, we have a snippet of the code for this case. So this is spring March system, which we are also applying a lift that will be sinusoidal. So if we convert it to a using simple Euler method that we have seen, if we convert into a two linear algebraic equation with two variables that we have here, yn and zn, and this is the code where, so this equation on the right hand side are directly written in the code here. All right, I have written those equation. So we are using simple Euler method. So one thing I want to tell you that this snippet on the code on the left hand side can be done in any C++. You can do it so you can do it in any C++ platform, or you can do it by C++. The only thing of the OpenFOAM that we are using is we are defining a constant scalar and scalar. So this on the left hand side, we are only using user defined data type of OpenFOAM, that is constant scalar and scalar. Rest is just simple C++ coding. There is nothing new from the OpenFOAM side, but we are solving it in a OpenFOAM environment. So now we'll jump into the coding part. So first you all, so let's go to the So I have already made the case and I'll just show you. This is a spring mass. You see spring damper system. I have already made this code. I'll show you. So this is basically I have written on myself. There is no open form source file or solver is used. Okay, so this is basically all by myself. So this is just to show you and how OpenFOAM does this. I'll show you in the next. So here you see we have a mass of 2 kg and scalar, so constant scalar. So this is user defined data types. So we have a mass of the cylinder or the body is 2, stiffness is this. Damping you can keep for now is 0. Damping is 0 and then we have constant label. So label is like integer data type of C++ and we solving it till let's say one end time is 1, start time is 0. Now we are defining scalar y old, v old, y is displacement, v old is old velocity, and time is time. So for now we are defining lift as 0. So the thing is, if we are defining this like constant scalar, you have to initialize it. All right. But if you are defining this like scalar, then you don't have to initialize this. It can dynamically change. So we are giving an initial displacement of 0.2 and initial time is 0. And for now, we are not adding any lift from that side. So the thing is, here we are, for now, we are just solving my plus ky. We have only mass and a spring system. And we can just solve it simply. It is not a big deal. I hope most of you guys are familiar with it. What we do is wclean dot all because it is already. One second. So you see wclean dot all, it is now cleaned. So I have already run it. So I am cleaning whatever and it to rerun again to show you guys again what we are doing. I'm just, there is something that is telling me there is some problem. Okay. Hold on. Just remove it. It was saying F was not declared in the scope. So okay, so there are some unused variable warning that it is giving me. So let's not go into that. What I'll just simply do this, I'll go to a run test case that I have made. So for this, yeah. So for this case, we don't need a test case, right? Because as I already told you, there is no mesh, there is no domain. It is a simple. So how to run it? There is some command to run it. Let me just tell you. There is one command to run it. Let me find that command. Wait, sorry for this. So this is the command. So as you already know in block mesh that this greater than sign and log will write the log of this. Okay. So now when we had compiled the solver, you know these things, right? So in the previous lecture we have covered it. I am just telling you again this. So foam user app bin. User app bin means it is making a user application whose name is Spring Damper, right? And it is making this using this C file. And in option, we have the library that we need to execute it. So the name is Spring Damper, right? So what you have to do is you have to run it here. You have to write the name of this. So it is run. All right. So let's see the output. So this log file has already written this command. So when we write this log file, this write whatever we want and output on the screen. You see. So if we have run it like just like this without this log command, you see it print out everything here. But since we have given this log command, so it is writing everything for us to plot, or you can do a lot of things. So you see a log file. So we can
Check there is a question in chat box.
so actually when I'm sharing the screen, I'm not able to see the question. Okay. So yeah, so actually I don't know what it is, but I don't know the depth of it, but it is a command to write the log file. So you can Google it. Like it is not a thing to go too much deeper into. So this is a command to write a log file. This is how it is done. So the basically when you run any application in general, you have to have a zero folder mesh, and then you have to have the set root case checked everything. But in this case, we don't need the zero mesh or the system folder because there is no mesh. Or this is a simple ODE. So you can look, you can Google it. Buju Srestha, you can Google it. Pratish, if you know it, you can tell him.
RKC is the, you can Google, you can see that this is a Range Kutta method. So this method has been used to solve this ordinary differentiation equation. Yes, yes.
Okay, okay. Great, great.
So this is a Range Kutta method. So you can see that there are different means numerical method has been coded in OpenFOAM that can be used to. So if you want to change this method, so like Abhishek has typed the RKC RKCK45. In that method, you can also type some other kind of method like RKDP45. That is the Range-Kutta ordinary differential method with the
Okay.
different. Yes.
So in that case, if we even if we don't use, it is not a problem because we are not using Range Kutta here. So thank you for the insight, Pratyush. So we
Yes,
don't
yes,
need
yes.
Range Kutta here. Okay, okay. So we don't need it here. All right.
So this is the method just. So he using the solver and he is passing an argument that is RKCK45. In that place, he can pass any other argument that is going to be used to solve the government equation. So I think it is clear too.
Yeah. So thank you, Pratyush. So the thing is, we are not using here Range Kutta. We are using. I'm just writing my own solver from the scratch. We'll use it Range Kutta and we'll use lot of solver in the next part. But for now, if we don't use this RKCK, it's okay. So just quickly see the result. You can always use GNU plot in Ubuntu. It's very handy. So you can see we are getting a sinusoidal behavior. The maximum amplitude is 0.2. All right. And you can also replot this is the velocity. So the maximum velocity is around. So here we have only mass and here we have only mass and spring. We don't have the damping. So if we introduce damping, let's say we introduce a damping of 1, we just give 5 minutes to it, not much time. Sorry, we recompile it and we update this GNU plot. So you see the peak amplitude is decreasing. If we further increase the damping, it will reach a critical point. Let's say, let's give like 100 or 200, maybe 2000 is a bit too much. So now we'll recompile it. So you know that in spring mass system, there are three kind of responses. First is uh, under damped, and then critically damped, then over damped. So what we saw, uh, so is under damped system just right now. So let's see what kind of system is this. So So you see, sorry. So damping is here. Let's give this damping 100. You see now this is kind of critically damping. It is going one cycle and damping. All right. So we can, if we increase the damping, it will go to a over damped system. Like it will not even complete a one cycle. So let's give it like 2000 just to show you. So see, if you want, if you see there is nothing like it is getting damped as soon as it is coming down. So the point is OpenFOAM, if you don't have the idea of C++, if you want to do something, OpenFOAM give you an environment to do any kind of C++ thing that you want. All right. So you can, apart from CFD, you can use OpenFOAM environment to do other things also. Need not to be only used for CFD only. For now, what we will do is we'll use a lift. So we are giving a sinusoidal lift, that is a scalar F is force equal to sine omega t. So here omega can be, let's say, 10. Oh, no, we can give anything. Yeah, let's give 10, no problem. And let's decrease the damping little bit here. This becomes like a forced harmonic oscillator. So let's see how it gives. Oh, also increase the time step, letting the time step to 100. Now we compile it again. Now we run it. Now you see the result. The force is too much, I think. Force is too much. Hold on. Uh-huh. So there is some problem, but you can see, hold on. There is some problem in the lift. So the thing is, I'm not sure. Okay. So we have to define it like this. So lift left is equal to amplitude, let's say 0.1 F. This becomes like 0.1 is the peak amplitude and F is like sine omega t, where omega of the forced oscillation is 0.1. Now it should give us good thing. So whenever, like, it is always good to do a wclean.all because sometimes previous things can hinder your current compilation. Still showing the same. So the thing is, this is scalar F is equal to sine omega t and lift is equal to 0.1 cross F. There is some divergence issue. So the thing is, this is diverging after, so it is not going to each time step. So this is diverging after some time. So we have, what we have to do, we have to introduce a tolerance. So we have added a while loop. Let's see if it works now. Hold on. Give me some time. So the code, the algorithm of the code is okay, but sometimes the timestamp, lot of things, tolerance, these things you have to see. So in some times it was working fine. Yeah, so it is coming little bit smoother now. The thing is, so when we add this lift force, so this should go to first, it will damp a little bit and then it will start oscillating with the force of the forcing with the force that we have applied. So this with this harmonic force, this should start oscillating. So I'll share this file. So this is just for you to show that we can do anything. So I'll just share this file. You can look into what is wrong with it and try. So the algorithm is just this, the divergence issue we have to see. So if we are not applying the lift, it is working fine. But with lift, it is giving us some problem. Okay. So when we start to debug, it will take a lot of our time. I don't want to do that. Okay, so you guys look into it. So you can look into it yourself. I'll share this file. You can try it out. So now we'll move ahead. Okay. So now we have seen that this is the code which involved only this constant scalar and scalar user defined data types of OpenFOAM. It does not involve anything, but OpenFOAM has a library. So this was a simple equation, right? So second order, that to a linear equation. You can also do it analytically. So what happens when we have higher order equations? So for example, if we have higher order non-linear equation, that is fourth order, then we have like Z1. So this, the fourth order equation, we convert to four number of first order equations. So we have Z1, Z2, Z3, and Z4, and we have these equation, all right. And what we can do is we convert this to a system of linear algebraic equation, and we get something like Ax equal to B. So this, and you know that this is solvable, that we can find the value of X, and so we convert this into linear algebraic equation. So now how OpenFOAM does this? So this is the tutorial from online tutorial in which there is a little bit of mathematical background, not so deep, and then it is we'll send the link for this also, no problem. So here it is showing how we can solve any ordinary differential equation in OpenFOAM. Here it has shown the full thing. The first thing it does is this mass of the system, okay, stiffness of the system, and right. So this is the class that is making my ODE, and then it is in the public parameters of the this ODE system. It has mass and the scalar, and then he is defining a constructor of this my ODE, and he is passing its address of the scalar, mass, and stiffness, and he is also defining the system of ODE system, calling a function which I'll show you in the just meantime. Then he is telling how many number of equations it has. So we have spring mass system is second order. So we have two equation. And then we have derivatives, and we have Jacobian matrix. Okay, so Jacobian matrix is basically the coefficient matrix, right? So like there is a full mathematical discussion on that. I have a PDF file attached that you can look into it if you want to go deep into mathematics. But since this is an open form session, so I'll not go too much into those things. So this is PDF that I'll share you. So numerical method of second order ODEs, it has a lot of things. It has also this Rangakuta. So there are different methods to solve a higher order ODE. So first is like the simple mass damping system. This is forward Euler. So this is one method. The forward Euler is nothing but it is derived from everything is derived from Taylor series in this. So this is a Hind's method, and this is your Rangakuta. So Rangakuta is higher order accuracy method. So when you want higher order accuracy, you can use it. So there is here it is here backward Euler, and here at the last, if you have like n number of equations, so you have to go to a matrix kind of solution. This is Cramer rule. Why guys all know that. So this is where the Jacobian part comes from. So I'll not go into too deep. So the thing here we want to learn is how to go through the open form environment when we are making our own solver. So first, if you are in terminal, you can always do like this. What? CD WMPRO project directory. Okay, so it is showing this is to CD project directory. It will go to the folder where now you do ls. It is showing you a lot of folders. So out of these, you want to go to the applications. Go to application, then do again ls. Now solvers. Now in solvers too, you have basic. So this ODE solvers are in basic solvers. Basic, not in basic, sorry. So the thing is, this looking at the folder through this terminal sometimes is not. So I am not used to it. So I usually go with this. Like in Ubuntu, you go to other locations and then you go to computer and you know that your OpenFOAM is installed in OPT folder and you open it. You go to application solvers. Aha, it is in test. Okay, so it is in application, then test. And you see something like ODE. Where is, oh, here it is. So here is your ODE solver. So I'm opening it. So in this ODE solver, it is, so there is no create field. This is the only one file for this. And you have this header files, argument list, input, output, ODE system and ODE solver. So this, it is calling ODE system.h. It is using two source, two codes from the source file, that is ODE system.h and ODE solver.h. So now this is defining a class first, test ODE, then this is the constructor of the class, number of equations, derivatives, this is the Jacobian, and then and there is whole lot of code here in which you define your mass damping, and here you see this is creating a pointer auto PTR ODE solver, and it is pointing towards the ODE solver. So this solver is in this header file. This is ODEsolver.h. So this is basically object pointer of this class. So you can always use a class to make an object. Here it is defining a object pointer. All right. So the main
Abhishek,
thing. Yes, yes. Hello.
so Right now we are in this .c file. So suppose
Mm-hmm.
if I want to find the location of ODESolver.h file, so
Yeah,
how can
yeah.
I find it?
I'll go to that part only. Yes. So that ODE.h solver and this, so where it is used. So the thing that we are, so this pointer here, just 2 minutes. I'll come to that now. This auto pointers, this object pointer is pointing to the ODE solver. And here we are using this pointer to call that function, that is solve xy dx net. So now we have seen two header files. Okay. So Rala will go to this. Pay attention. So now in this also, now we'll go to OpenFOAM 7. You can always go to the terminal through this, because I'm not like, you can always try it, but I don't like it much because I want all the files. I want my files to be in front of me. So we go to source files. All right. In source file, we look for the ODE. Yeah. The source, so everything that we have here in this code is in the source file. So we go to source file, and then we have this make file contains the file and option files. And this is the code that the like this is the compiled the object files, or we can say yeah, compiled object file. So this is the 1010 code that is after compilation, which is this application or solver is using. So in this it is calling, which is calling this ODESolver.h. Okay. So this, it is calling the ODESolver.h. So if you want to look into this, how, what is, if you go into ODESolvers, so this is the main file. So ODESolver.h. Okay. So this is the main file. It is calling another file, ODESystem.h. So this is the thing with OpenFOAM. As Pratyush has told you the things about object registry and like abstract class, base class, and how the hierarchy is going on of inheritance. So this ODESolver.h is again calling this ODESystem.h, which was also used in this ODESystem.h. All right. So the thing is, here we have some variables, and so we wanted to focus on which function we were using to solve the ODEs is this solve x, and y, and then dext. We have we have a function which has four inputs. Here we go. We look for ODE solver. So let's also open it the C file. So here have a function you see solve, that is similar to this solve. This function is in this file. Okay? And you see the thing of polymorphism here, that is you can define a function or a constructor, like you can define it many number of variation you can have. So here it is calling only three variables. This solve is calling three variables. This is using a solve function which has four input variable. So which is, so this also has three. So this is the case. This is the function that we are using. All right. And you can see it is doing all these things. So this is where actually the OD is being solved. All right. So we have to always look how many inputs our function is having. And in like there are three functions of solve, same function of solve. And in that we have to see which function that our code is using. So our code is using this. So in this also, if you go deep, so there is one thing like scalar dx try is equal to. So yeah, so it is using a step state. So it is defined. It is using a function of. So it is, I think, defining a class somewhere, and then yeah. Hold on. So this is object, that is step state, and it is using a function. this. And in this function, there is a lot of things that are of which method you want to use. And because if you go into this file, you have adaptive solver, you have Euler solver, Euler SI sum solver, then you have Range Kutta 45, Range Kutta higher order, maybe more higher order, and you have all these trapezoidal integration that you guys know. So these are all different kind of solver. All right. So in this, which we are using, you have to find out. All right. Like you can go and keep like, so this step object that we have. Where did it go? So this step object there, this step state that we have in this step object, it is utilizing a lot of functions. Step dot dx try. So step is an object of, I think, step system, and it is using a lot of things. So the thing is, one file is this, other file it was using is system file. So you go to this and you look into this .h file. So here the definition of the Jacobian is here. So when you go into OpenFOAM environment, so this is very simple. So, but even this will take you like a day to understand how the things are going. Like, all right, so OpenFOAM is not very simple, but once you get the hold of it, what kind of data types it have, how it is using polymorphism, how it is registering the objects during the runtime, and how the different files it is exchanging, how many objects it is creating within the file. So this ODE solver is using the object of this ODE system. Okay. So now I have shown you that this ODE solver that we have here, this is test.ode. Okay. So the ODE solver that we have here is using these two uh, files from the source code, and these are already compiled. So it is using these, and it is writing its own short class, which is to give input to the solver. Okay, so it is giving input to this solver. All right. So now I think most of the things are clear. Someone asked me. I hope it is clear. Now we'll just.
Abhishek,
Mhm.
uh, can you show us how to use that iname command to find the .h file location from the terminal?
So is there such command? So there is a command of grep. I think, yeah. If you know, you can tell me, but I don't actually. Most of the time, I have the whole idea where the things are, but there is a command grep. You can Google it. So there on OpenFOAM, you have a lot of commands. If you are regularly using OpenFOAM, you have to have the knowledge of these commands. Raghavendra Khadge, you are, I think you asked this question, right?
Yes.
Okay, okay. So if you know, you can tell me. There is one command I know that, but I have not used it regularly, but you can use it. So you see, using how to find a file using grep command. So these are things that you can look up to yourself, like uh, this is just a simple command. You can always navigate through different files using this command.
Okay.
Yeah, so like if you want, like I'll take 5 minutes, but I have a lot of content to cover. So I think this was in the first class, it was uh, like covered by Pratyush, like how to use grep command. So yeah, I see there are a lot of options that you can use to search any text file or a lot of things. So my thing is like if you know the name, so you were telling what underscore name command.
Yes.
Yeah, there may be a lot of commands, man, because in Linux system, when the system changes, command also changes sometimes. So there may be an user-defined command for OpenFOAM that I don't know, but I usually like navigate through this because I have worked it on like 6 months or 7 months, so I am familiar with this.
Okay, okay.
So you can ask tomorrow Pratyush, like he's more expert on this.
Yeah,
Okay.
sure.
Yeah. So now we'll just quickly run the ODE solver and move to the main task. So this solver that I have already made, this ODE solver. So this solver is basically same as the solver that we have found here uh, in this application, then test, then ODE. So this solver is the same solver. Here we are solving the same spring Mars damper system that we have solved just now. And I have just, because you have to write each and every coefficient of the Jacobian matrix here. It talks later a lot of time. So I'll just quickly run it. It is very simple. You can look into it. I'll share the files. This is the ODE system. I will just same thing. 1 second. Clean the previous files. And then we'll do wmake. And now someone asked me a question. Now you have to choose your. Okay. So what was the name of this solver? We have to look for the name. What was the name? So name is, these are include files, my ODE. Basically, these are the files that are required to compile it. My ODE, my ODE. And then we have to select which, which solver you want to use. So source files, we go to source file and then ODE, all right. Then ODESolvers. You can use any of these. So RKCK45 will use first. Because it gives us results. And now it is giving something else. So it is saying these. So okay. So it is saying I have typing mistakes. So it is saying valid ODE solvers are 13. Euler SI1 RKCK 45. So RKCK 45. Just please see the log file into GNA plot. You see, it is same always, so there is not change. So let's change that solver to different solver. It is saying which solver to use. I think we should use this Euler solver. Let's see. Because we solved our previous problem. This is the same problem that we solved previously, spring mass damper system. Nothing, there is some mistake. But it is saying integration step greater than maximum 1000 extra. So it is giving us some issue. So let's not go into that. Basically, you can solve it. Let's try with someone else. Just for the fun of it. SIBS. It is working. Some solvers are working, some are not. So the results are almost the same. Then there is no change. So basically, we have told you like how to navigate, how to see things, and how to solve an ODE in OpenFOAM environment. This was just to give you an introduction. Now we'll move ahead. Now we come to how to make our own CFD solver. So now we also have mesh. So we have to have a certain case, control dict, PD files. So first and foremost, these are user defined data type that you have to like keep in mind. So Boolean label is like integer of C++. Then there is scalar. Then there is char char in C++. We have a word, and there is also string that is quoted text. And there is list. Vector is vector like 3, which has 3 values. And for example, you have a vector, let's say you have a mesh vector, its name is mesh. So you can access the x component of that vector using mesh dot x bracket. All right. So similarly, you can, for a tensor, you can access, for example, if mesh is a tensor, you can access it using mesh dot xx bracket. So you can always use the components of this tensor and vector. So dictionary is also a user defined data type. So now we have a lot of geometric fields. For example, for internal fields. So there, so we have a mesh, we have a face and control volume, and we also have data points. So volume scalar field is for the cell volume, which don't have a vector. Then there is volume vector field. So volume scalar field is like temperature. You can say temperature or any other scalar variable that you have. Then you have volume vector field, which is like velocity, which have a vector and which is defined at the control volume, that is control volume center. And then there is surface vector field, like which is a vector defined on the surface scalar field. Then you have surface vector field, and these are for the face centers, discrete face area vectors. So like these are the class of geometric field types that you have to keep in mind. So for if you want to study this more on this, I'll share the PDF file. So you should go through a basic, you should go through the programming guide of OpenFOAM. I think I have, yeah, it is. So everything, the basic that I have told you till now is here. Okay. So here it is saying, you see the definition of the coordinate system it is defining. Then in programming guide, it is telling you about the tensor, how the tensors are defined, and tensor operators, how many temperature. So basically this will tell you all the basics about the how the operations of tensors and vectors are done. If you go into here, these are the dimensional and units, how to define a dimension. So the chapter 2 is important, which is important for this, that is discretization procedure. What are the different discretization procedures? So first we have del operator, then we have gradient. The thing is, so this is a scalar transport, the temperature equation. So in this you have operator. Okay. Yeah, so here it is. So this is the Laplacian convective term, and so this is you showing the temporal discretization. So in which basically we have this, this is like del phi by del t k divergence of phi. So we have divergence, we have a gradient term in Navier-Stokes equation, and we have gradient term divergence, and we have simple curl also. Sometimes when we have to calculate the vorticity, we have curl also. So this file you should go through chapter through completely. First, it is telling you about the differential operators like delta, and this is the gradient. All right, this is the gradient term, which, like if it is a scalar, it will give you, if you take the gradient of a scalar, it will give you a vector. And if you take a gradient of a vector, it will give you tensor. So this is the divergence term, this is curl, this is Laplacian, and this is how the temporal derivative is done. All right, and this is spatial discretization, temporal discretization is telling me. So this, so basically for any system, we have this. We have a time derivative that we call, I think, material derivative. In this we have the advection part and the temporal part. the advection part and the temporal part. So it is using a gradient del dot phi. All right. And then if you go down, 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 it will tell you how the patches and the faces are defined. You should read it carefully, like you should go through it carefully, very carefully. I'll show you one or two test cases that is okay. But if you want to work in OpenFOAM, you should have each and everything clear of this chapter 2. Even also chapter 1, but chapter 2 is more important. So it is telling you waste all the geometric field types. So basically, you always have to solve the AX equal to B equation. So if you come to the PPT, so this is, so when you have like any equation, let's say you have this equation. This is the Navier-Stokes equation. So in the end, for example, a particular this scalar transport equation, what we will get is AX equal to B, where X is what we want to find out. We want to find out the temperature at every mesh points, and A is the coefficient and B is on the right hand side. So this is the final equation that we get. X is uh, S is we want to find temperature at every grid point. A is the coefficient matrix and B. So like in some, you must have heard about the implicit and explicit discretization. So I'll quickly take you through the discretization part. I'll go to the chat GPT. So you just write here how to discretize, how to discretize the transient 1D, let's say 1D heat equation. Let it take its time. All right. So basically, I want to show you what is the meaning of this. So when you go more down into this, you'll find one thing that is very important and frequently used, that is this, this finite volume method. So when you discretize, you have two methods. One is finite volume method and one is finite volume calculus. I just want to tell you what is the difference between the two. And for that, you have to understand how we discretize. So, so this is the time discretization, you see. So we use implicit back. So I told ChatGPT to discretize 1D steady state heat equation in which del T by T is temporal term. This is conduction term and this is heat generation. All right. So it told me that uh, for the time we have Euler discretization, that Tn plus 1 is the forward time that we want to calculate, and Tin is the that we have already calculated in the previous iteration. So now it is doing the spatial derivative and it is doing central differencing. But the thing that we have to pay attention is it is considering the n plus 1. So it is considering the temperature that we are going to calculate, not the previous one. So here it is telling me that it is we are using implicit method, implicit Euler. So here, if we want to do discretization like this, we have to use FVM, finite volume method. All right. So the chat GPT has done this using the implicit, that is when it is discretizing the terms on the right hand side. Beyond accept this time temporal term, when it is using the term on the right hand side, it is using the forward time, that is n plus 1, not the n. Now I'm telling chat GPT, do this by explicit method. All right. I hope it understands. So when it will do it by explicit method, it will discretize this term and it will write here n. What it is saying, you can always use chat GPT for simple things. This, you see, now we have, when we have told it to use explicit, then it is using n. Means it is using the time temperature from the previous time step or the previous iteration. So this is the difference between, so this n plus 1 terms always go on the left hand side. That is, it needs to be calculated. This b terms go on the right hand side. So these AEAW becomes the this coefficient part, that is the big A, and this x, sorry, this x becomes the Tn plus 1 term. All right. So when we use FBC, that thing that is with like T and N, it goes to the right hand side, that is the B. And when we use FPM, it goes to this A. The coefficient, the value goes to X and the coefficient goes to A. So this you have to keep in mind, that FVM and FVC are like there can be things broadly it is implicit and explicit. All right. For example, time, you can do implicit, explicit, second time derivative. So divergence, you most of the time do explicit things. Okay, so to make sure that you go through this file very carefully, don't miss even one thing, because if in future, if you are skipping some things in this file, and in future, if you are going like without reading this, if you are start learning OpenFOAM, then you will face some problem. And again, this is the Laplacian term, how to discretize it. We have volumetric term, we convert it to like surface vector. And all right, so this is the convection term. We use central differencing. So this, where it is defined, the central differencing, this is defined in FP scheme. This is time derivative, and this is you can see, you can use either forward or backward differencing. Sorry. And this is a divergence. So you can see how everything is discretized. All right. Grades your curl and everything. So now we'll open to this is temporal discretize, how it is done. And now it is discretizing a simple treatment of temporal discretization OpenFOAM. It is considered, let's say this is like 1D heat conduction. All right, so it is solving FBM dd by dt phi kappa FBM Laplacian of phi. Okay, so it is using fully implicit. All right, so there is everything is implicit. There are boundary condition. Now it is using examples. Okay. Now we'll also go into some examples. One second. Now where will we? Now we'll directly go to, so what we have to do is, so this is week 4. Let's change to this test for you guys. Week 4 we have a test. Now what we want to is, so when we go to solvers, again we are moving to the solvers. This is SRC. We are going into application and we are looking into the solvers. So we want to know like make our solver for 1D heat conduction, 2D heat conduction. So we go to the basics, and we go to basic, you have this Laplacian form. So this Laplacian form, this is discretization of, this is diffusion equation, sorry, no, not Laplacian. So let's go to scalar transform, have a look at it. Okay. This is scalar transform equation. That is this one. This is Taylor transport equation. The first is temporal term. So you see, so this, so how this code works is, now these are the header file, basic header file. So it check the case, like check the cases, create object for the time mesh, and then it go to the create field. Then when we go to the create field, it shows this that we have to that there is a volume scalar field, that is temperature. So the temperature is defined at the cell volume, that is cell center of each control volume, it is defined. So it has a runtime, like it object is defined, and it is object registry is also done during the runtime using the mesh. And input output object, it should be always read, and it should be auto written. So sometimes it is this input auto object, instead of must read, it is written read if modified, or no read, or in write it is no write. But here we are saying you should always read, because it is changed every iteration, and you should auto write it. All right. Now we have volume vector field, that is u. So u is like constant. We are not solving. So I want to make I want to tell you guys that when we are only solving the transport equation, we are not solving v. We are just giving it a constant value. So we have a volume field, all right, and then we are telling it input output dictionary, the variable that we have already created, to go to transport property. All right, then read in that transport property, read this diffusion. Okay, so we have called this create field.h. So this create field is basically creating the field your u, v, p, all the field volume or scalar field or the phase field in some cases that you want, you have to define this in hash create fields.h. And then it is to this simple loop. Then we are defined a coded number because we have time involved in it. Then we have this while simple dot loop is so when then we have this where this is where we are solving our equation, right? So we are saying while this loop is running, we are saying that while this simple dot loop is running, like this is the time loop. Simple loop means the simple loop simply means that you have given a time step. It will keep on running the simulation keep on running till a steady state is achieved. Simple is only for the steady states. So you will all find piezo loop when there is transient simulation. So you can look up to this simple loop how it works in like open form. Simple here we have. So when the simulation start, this is how our matrix AX equal to B is made. So we have finite volume method. Okay, so we are implicitly define everything here. FBM DDT of T, that is this temporal term. All right. Then we move to the this advection term. So phi is our advecting variable. Most of the time it is velocity. And we're also discretizing it using the finite volume method. And then we have at the end the diffusion equation. And we are also discretizing it using the finite volume method. That is Laplacian of this time, and dt is the diffusivity. All right. Now we'll also introduce you the FPC. So now let us solve the 2D heat conduction. Second. Now I have made a folder. Now we'll go to the application. Week 4 test. Now here what we'll do is we want to copy that transport. You can copy anyone. So let's copy which this and out of this basic. Let's copy this Laplacian form. All right. Or let's copy this potential form. Let's copy the Laplacian form. You can copy anyone like CP minus R WM project directory. Then we have application. basic applications or basic flashing form to which folder? Now we have to find the destination folder. Form. Home app means home application. In application, we are where? We are at OpenFOAM 7. Sorry. Okay, we are already in the test, so we have to do this. Okay. Okay, we have to name it. So let's name it the heat conduction. Let's name it 2D heat. So we go into 2D heat, we open everything that we have. All right. So we have this Laplacian form. Okay. So we have to convert this to two transient equation. So let's open create field. Whenever you copy a solver, the first thing you want to do is you want to look at the options, like which are the already compiled file that is it is including. So these hash include this include files are which are already compiled, and these are the library location of the library that we are using. So like this is the location and this is where these compiled files are there. You want to first look at into this. Then the first and foremost important thing you want to do is you want to change this to user append. If you are not using this, your basic code, the main code of OpenFOAM will be changed. You may face a lot of problems. So I am naming this as 2D heat. You can also name this 2D heat. It is big now. Okay. So now you have to change this name also. 2D heat. Let's open it. So now we have this everything I have already explained this a lot of times. Now I'll jump into this simple loop. So simple loop means solve till steady state. Now we are getting this info. Then we have FV scalar matrix. Why it is telling a scalar matrix? Because temperature is a scalar. Now because this was the Laplacian form. All right. So we have a transient term, and then we have Laplacian of temperature. So this was like 2D heat conduction equation. Okay. All right. But so first we'll look into the normal 2D heat equation. So what we have to do is, we remove this FB option. There is no need of it. So we can directly say this as 0. And what we do is we also remove this. Okay. So what we did is we have only the Laplacian term, that is del square T. Where is my chat GPT? So yeah, you see, we have only this term, del square T del x square plus del square T del y square. Okay. This is only simple 2D heat conduction, no transient term. So here you see finite volume matrix. There is no use of this implicit explicit because there is no time right now. But and this always returns a matrix. So yeah, so it is good for to use FBM here. Now we'll just compile it. Now we have changed the name it to 2D heat.c, and this name is 2D heat. Okay. Now we'll make it w clean dot all. It's giving me some error. Hold on. This must be some kind of syntax problem. So we can check the syntax by looking at this. Okay, 1 second. I think it should be FVC. Yeah, yeah, it's it was like a very bad one. Hold on, hold on. There should be a. Okay. So this create FVO. So the thing is, this labelation form is a little bit for the advanced problem, and ours is very the basic one. So we don't want this create FV option here. All right. So what the thing is, we just want to solve it. It is what it is doing. It is defining AX equal to B problem using this FB scalar matrix. It is T equation. It is defining the T equation, that is AX equal to B, the whole matrix. And then it is using the FB option constraint, and then it is solving here. All right. So because we are for now, it is the simplest of the problem. So we'll discuss these FB option things and T equation dot solve that is used in the more advanced solver, for example, simple form or pimple form, piezo form. Today is very basic solver. So we'll just remove everything that we have here. All right. And instead of this, uh, we just write solve. All right. Let's see if there is no syntax error. Yeah, so I think it is everything is fine. So solve, I think S is small. Yeah, it is small. Hold on. We don't need this zero actually. This is only needed when it is run. So when you have only one term, you don't need to write zero on the other side. When you have multiple terms, then you might use it. Okay, so now we have made our 2D heat conduction solver. So we have solved this equation. That is where it is. This is basically 2D heat conduction. Del square T, del S square plus del square T, del Y square equal to 0. Now we'll run the test case. Now we'll move to the test case and we'll go and run it. So I have already made a test case of 2D heat conduction. In this, I have already run. What I'll do is I'll foam clean PUTORIALS. So one thing I want to tell you guys, if you are not parallelly doing it, or understanding it, you will just lag behind. So I hope you're parallelly doing it. And also home clean polymesh. So now in this case, we have a simple geometry. Uh, if you I open the block mesh tick, we have one block. All right. We have one block that is like delete cavity. We have X min, that is the left hand side wall, right hand side wall, and front, like we have four walls and front and back is empty. This is our block mesh. How we have defined a temperature condition is on the left boundary we have 400, on the right boundary, on the bottom boundary we have 350, and on the top and the right boundary we have zero gradient. All right. So now what was the name of our so now we'll run this problem. I hope you understand what the problem is. I'll share all these test cases, so you need not to worry about it. You can always always use this test case after this session. Now what we have to do is, what was the name of? We have to run first block mesh. Now 2D it. Let's run it. Now we'll go paraform. For those who are a little bit at advanced level, these things may seem very simple to you. So you can always have a look at this or the recorded lecture if you are getting bored. So now let's run it. There should be some change. One thing. Okay. So now it is converged. You can see if I show you, you can see the value right here. We have 400 and 350. At the bottom, we have 350. On the left, we have 400. And there is a equal gradient throughout the. So you can see that you can always plot like temperature distribution in the vertical middle or the horizontal middle, that these things you can do. Now, if you want to look at the patches, you can also show patch names in the mesh groups. You can see everything. So here you see X min is 400. You can always also see the values. There are a lot of things you can do. So that X min we have 400. At the bottom we have 350. These were the boundary condition that we applied. Now what I want to do is I want to use the FBC. So in this FBM, everything is implicitly. So if you want to teach you the difference between FBM and FBC, I have to add this transient term. Okay, and I have to add this the heat generation term. So I have already done something. So this equation. So in just pay attention to it. So this is by default, it will be done implicitly, forward Euler. So we want to do this by implicit method, that we will assume that these temperatures are at Tn plus 1. That is the time step that is the temperature that we want to calculate for the next iteration. And this Q terms is constant, like Q is heat generation. So then this output is always a scalar. There is no vector output from it. So we'll use FBC for this. You should not, you can't use FBM for this because there is no independent variable in it. So wherever there is heat generation, or for example, there is some kind of constant pressure acting, whenever there is any kind of source term in any of the equation or any of the dynamical system, when there is source term, the source term is always discretized using the FVC. Just keep in mind that. Never try to discretize a constant like a source term using the FPM. So I have already written the code. So what it says is that del T by del T, this FBM ddt by T means del T dou T by dou T equal to del square T by del X square plus del square T by del Y square plus Q, that is heat generation. And I'll just copy paste it. I'll just copy it, and what I will do is I'll just copy it. All right. What we have done is, so we have introduced a heat conduction part, heat generation part. Okay. So now we have introduced the heat generation part. So now we'll try to compile it. So Q is the heat generation. So it is throwing us an error. It is saying that the Q is not declared. So in this case, what you have to do is you have to go to create fields. Now info, we are reading the transport properties here. All right, transport property. Now what we have to do is, so here it is reading the transport property. Here it is defined a dimensioned scalar. A scalar which are dimensioned dt. Here we'll add one more variable, that is dimensioned scalar q, that is heat generation. And we'll compile the application or the solver again. Now our solver is compiled. So now go to the test case. Now we want to clean everything. Foam clean. You see everything is cleaned. Now we use foam clean polymesh. It's also clean. So now we'll run block mesh again. We need not run block mesh or clean polymesh, but we are doing anyhow. So we'll run the 2D heat again. So you see it is giving me an error that what? It is giving me an error that it is telling me that what? Incompatible dimension for operation. That there is incompatible dimension for the dt. So we have did some changes in dt part. Yeah, so let's comment this out for now. And it is saying us incompatible dimensions. Okay. So the dimensions for dt's are okay, but it is giving us one thing. Let's see. Yeah, so dimension scalar. These kind of silly mistakes, please avoid. Don't be like me. We have to compile the solver again. You had to change. I didn't forgot to change here also. So now, well, we'll run this again. It should not. Now it is giving us keyword. Q is undefined. So now we have added a one more variable. So we have to uh, add this variable, that is Q. So now what is the dimensions of the Q? So for the dimension of the Q, you have to go. So OpenFOAM by default solve this equation. On the left hand side, we have only del T by del T, that is Kelvin by time, that is second. So we have this dimension, and OpenFOAM by default uses this equation for any, be it momentum or energy or whatever, any equation. So here we have Q by rho Cp. We have to give proper dimensions to it. Okay. Otherwise, it will throw us a problem. So we have defined a Q. So let's give var dimension. So if you think that Q is heat generation, so let us give the dimensions of heat generation, whatever they are, it will give us, it will directly throw you a problem like an error. So you have to make sure you see incompatible dimension for operation. The thing is, this dimension that the even the Q is heat generation, we have to give the dimension according to this equation. All right. So here we have Q. Delete this. Keep the previous one. Heat generation. How much heat generation we want? I have tried it, so I'll give a lot of heat generation. Now run it. Now we look into how things are changing. We are only interested in the last time step. This is a transient simulation, so but it is getting steady very early. It is converging very fast. So you see when we didn't have heat generation. So what our boundary condition was again? Let's see. Our boundary condition was on the left boundary temperature is 400. On the right boundary temperature is 350. All right. This was our boundary condition. Not on right. At the bottom we had 350. On the left we have 400. Now you can see if you look into here, the temperature has reached 30 like 3500 or some 350, and this is like 6300 or something. Temperature is very high. Basically, now due to the heat generation, and there is on the right and the top we have we have like adiabatic, what we say in which boundary condition, like we have zero gradient boundary condition. So here we have zero body. So all the temperature or all the heat is concentrated in that part only. In the previously we had maximum temperature on the left boundary, but it is now both shifted to the right. So we have added a like heat generation to this. All right. So this is how it is. We have solved transient term. We have solved the this viscous or diffusion term. This is diffusion term. This is transient term. We have added a source term. Now the next part is to simulate a advection term. All right. So I'll just simply add an advection term to this. Okay. So to add an advection term, we'll go to this discretization procedure. Advection term is basically your 1 second. Yeah, this term. All right, del dot u, what is this? This is advection term. It is that is. All right, so you can go through this. You'll find a discretization term for advection equation. So how we do it? I just simply go to that. So here is the scalar transform. Scalar transform form. I also made a 2D convection diffusion. So I'll have to go to this. So here you see, so we have to add this FBM divergence of phi t. So here phi is like phi is what? Phi is u or whatever the thing that is the t is a scalar, phi is velocity. Phi can be any advection variable, but here it is velocity. So we'll just simply add this thing to this solver, or we can also so we copy this, and my heat form, it was this 2D heat. this was. So now we have all the term that you need for a scalar transport equation, that is transient, advection, and then we have Laplacian, that is diffusion equation, and then we have a source term. Now we have everything. We'll just run this. First we have to, so what it is telling us, that is there is phi is not declared, because in this create field we have not declared. So phi is also a volume scale, volume vector field. Phi is most of the time is velocity, so it is volume vector field. So we have to define a volume vector field. EEC, volume vector field, right here. Phi, compile it again. So it is different case, I think. Sorry. 2D convection. This is the create field. Sorry, it was the different file. So this phi is a vector field. Phi. So it is used at runtime and is registered, and we want to must read and not write. Even if we do not do not write it, it is okay, because we are not uh, because phi will be constant. So for example, we'll give an inlet velocity that is constant, because this is, we don't want to solve for u also. That will be a different problem altogether. Okay. Volume vector field. Okay. Vector. Okay, so let's go to the transport. So whenever like you're kind of stuck into what is wrong with it, because you may do a lot of mistakes in syntax in your beginning time, you should, it is always a good idea to look at the basic cases. Transport. So what we are doing is okay. Info reading vector field, volume vector field. Okay, we just copy paste and do this. Okay. And then what it is saying is there is some error in the function. So this is basically a syntax error. So syntax error are not of, it just takes practice to solve them. So I am writing this u field. Here I am, instead of phi, I am directly writing u, because phi is basically u in our case. And now I just again w make it, compile it. Again, it is showing some problem. Second. Okay, hold on. So let's just go with this solver. I don't know what mistake is there. Okay. Divergence of. Everything seems correct. I don't know. No matching function to call for this. So basically this is an dot C61. So this is a problem in this. Okay. So I'll just replace it with this for now. I don't see a problem. Okay, okay. I don't know. The thing is, I have already made a solver 2D heat conduction. I'll share it to you. So right now it's already late, so I'll just quickly show you that. You see here we have this is here we are including transient, this advection term and convection term all. So you can just W make it, so it will build a solver. I have done some mistake. One second, one second. So guys, it's already late. Sorry for this delay. So whatever the error we are getting here, I'll resolve it tomorrow. I'll take just 5 minutes to show you this final test case, and I'll share the rest of the cases. See if you guys have any question except this one. You can ask me now because it's already late. So it will just take 5 minutes. We have to show this, like identify what this error is exactly, and will. So this is basically a syntax error. We have to identify it where I'm doing it. And in the next class, first thing that we will do, will take 5 minutes and cover this. For now, if you have any questions, so if you are, if you have done the basic OpenFOAM, you, this is just a basic part for you. But I suggest you guys practice these cases so you can get a hold of it. So this is enough. This is it for today. If you have any question, please ask one by one. If you have any question, please ask me. No, no, sorry. I did a mistake there. FPC is not dealing with the constant term. Constant terms are by default are going to the right. That was a slip of tongue. Sorry for that. So for example, the source terms will by default go to the right. You don't need to use FBC for that. So when you are using implicit, then you use FBC. So we didn't have the time to compare FBM and FBC. You can do it yourself, or if you want, we can cover it in the next lecture. So the thing is, we'll take a problem. So auto PTR is basically, so there is one thing in classes, one thing is that object, like which when we define an object, we have access to the all the function and parameters of that class. So auto PTR, I think it was due. I think Pratyush has covered it in the first lecture in the user defined function. So auto PTR basically a pointer which is pointing to a pointer object, pointer to an object. So basically, instead of defining an object, it is it is having an address of that object. So pointers are basically variables which contains the address of that any variable. So here auto PTR is an object pointer. So here it is always good to use a basic simple object and use the function and parameter of that class, but in the simple form. But there are some cases where auto using this pointer is better. For example, where you have a lot of data to handle. So how to make a source term time dependent? Uh, Source term, yeah, you can make that. So if you have a source term, so you have to then you have to use FBC. Then you have to include into the discretization part. So if you have if you have a temperature which is like AX plus B, all right. So if you have a time dependent temperature, like your temperature is varying with time, then you consider using FBM or FPC. You can use either one of them. But if your heat generation is okay. So if your heat generation is increasing linearly with time, then you can use either FBM or FVC. You can use both. So if it is space dependent, then you can just simply you then you have to use that you have to use some of the utilities that you have. So you have to give this information the dict file. If it is increasing with yeah. So in the next class, I'll do one thing. So I was stuck at this point. in this advection part. I'll cover this. I'll take 20-minute class. I'll cover this aspect and also the mistake, like the error that we were getting. In the next class, we will cover convection, advection, and we'll see how the heat generation, uh, how to like discretize the heat generation term if we have a space-wise and time-wise dependent heat generation or source term. The thing is, you can always give a source term using the dict files. So you can define a zone, you can give a source term. There are things that you can do. Jamshid Moradi, so when you want to discretize it and use it in, so this FB option part will cover later, man, because it will get too much. So FB option we use usually when we define heat generation or source term in the like dictionary. We don't directly code it into the application part. Like we don't directly code into this. We don't directly code into this. All right. We write here plus FB options, and we whatever the changes that we have done in the dict file will like automatically discretized here. But because this is very basic part, and here we want to show you everything at the solver level. That's why I use that queue, that is heat generation. So this will come later, man. This FB portion part, FB option part will come later. Don't worry. Yeah. So this is only the basic of how to modify your solver. So I went to one by one transient term, heat conduction, then added heat generation. Then I was going for advection, but it gave some syntax error. So we'll take 5 minutes in the next class for that. So it will come, yeah, in the next, it is coming. Don't worry. FB option will be covering. Yeah, yeah, no problem. The next class shall take 20 minutes and do these things. I hope this is any other question from anyone else. Yeah, yeah, sure. You too. And now you guys start thinking of your project because we have reached to a point where we have started modifying the solver. So you guys start thinking of your project topic. Thank you, everyone. That's all from today. Okay, you can leave now. Hello, Pratyush. हॉस्टल के कहाँ गया था बहन? तो लास्ट के 10 मिनट में दिक्कत आ गई थी यार. बंद कर रिकॉर्डिंग. भाई डाल मत दियो ये.